everyone. I'm Emanuel. I'm Director of Institut Pascal, and I want to wish you a very warm welcome. Today is an important day because, not because of me, but because we have the chance to host Kerry Emanuel, who is here. And when the organizers knew Kerry was coming, I heard a feeling of great joy because he's one of the fathers of our field and has made incredibly significant contribution. But I will let Susanna introduce Kerry, and but I'm also very, very happy to have you here. Susanna.
Good afternoon, everybody. It's my pleasure to introduce Kerry Emanuel, who needs no introduction, as he's basically the father of tropical cyclones. He received his PhD from MIT, and after a very brief stint at UCLA, he spent his whole career at MIT, he's currently Professor Emeritus of Atmospheric Science. He received many awards, including being a member of the U.S. National Academy of Science, a fellow of the American Meteorological Society, American Geophysical Union, and a foreign member of the Royal Society. It's my great pleasure to introduce Kerry Emanuel.
I can get this to work. Thank you very much, Susanna. I have problems with the microphone here for a second. Sort it out. Can you hear me now? Okay. Well, it's a great pleasure to be with all of you here today, and thank you to the organizers for inviting me to this beautiful place and with a really great collection of scientists to start off the week. I thought that my job, since I'm speaking first, is to kind of introduce the topic, which I broadened out a little bit. So I called the topic overview of Medicanes, polar lows and subtropical cyclones, although I think we could even add some to this class. So I want to try to start a little bit provocatively. I think that the storms we're talking about, at least a subset of them, all belong in some very similar class. So I'll introduce what I call Rogues Gallery of cyclones, starting with polar lows, Medicanes, subtropical cyclones, and Kona storms. And there are probably many, many other regional names for this phenomenon. This is the four that I happen to know. And I want to suggest to you here that they're all the same, that they're not different, that we are a geographic species and we like to assign geographic names to them, like hurricanes for the Atlantic and typhoons for the Western Pacific. But physically, we're all physicists, we're talking about the same thing. I'd like to suggest that. I pose that as a hypothesis. One of the hypotheses that you might say would come out of this meeting would be, these are all operating on the same physics, and as a class, they all deserve a single name. Now, if I am able to convince you that there's merit to that hypothesis, then I propose a challenge to this whole group that we come up with a name for this class of cyclone, okay? That we don't have to refer to them all as completely different phenomena. Just as we have tropical cyclone as a generic name for these storms in the tropics, we should come up with a similar generic name. I'm not going to propose anything. I tried, I couldn't succeed, but you can. So I'd like to propose this as an outcome of this meeting, provided you agree with the hypothesis, which you might not, in which case you don't have to participate in the naming exercise. Okay. And I think it's best done by an off-campus exercise. That's my personal opinion. So here we have the four classes. I'm going to begin with polar lows here and just show you some examples. So here's a polar low up quite far north of Scandinavia, the Barents Sea in 1987. Beautiful picture, very characteristic. You have a tropical cyclone-like phenomenon. It's smaller in scale. It has an eye. It's surrounded by convection. This is cold air outbreaks over relatively warm water. It's not absolutely warm. It may be 5 degrees centigrade in this case, but it's a lot warmer than the air. Now, if we go to an ERA5 reanalysis of this situation in February of 1987, we see that at the surface here, we have, and the reanalysis does actually capture something in about the right place. It's, I think, quite remarkable. It's a very tight, this is 950 millibar geopotential, very tight closed contours. And if we go up to 400 hectopascal, so we're nearly at the tropopause at this time of year at this latitude, we see a closed flow, okay? That's a cold core cyclone. Now, this is the important thing. We're here looking at, on the left, again from the ERA5 reanalysis, the potential intensity. Now, most of you here probably know what I mean by that. I haven't decided to pause and tell you what that means. It's a thermodynamic limit on how strong the surface winds can be in a tropical cyclone. And tropical cyclones, and I would maintain this particular class of cyclone, are driven fundamentally by a thermodynamic disequilibrium between the surface and the atmosphere. And I would all encourage you to go back and read some of the beautiful papers written by the French physicist Ilya Prigogine some decades ago about how, in a whole variety of physical and biological systems, thermodynamic disequilibrium gives rise to organization. Okay, it's really important work. Most atmospheric scientists, at least outside France, don't know about this. And I think it's very profound and very applicable to this. So one other important thing that comes out of understanding Prigogine's work is you need a finite amount of thermodynamic disequilibrium to get organization. This is not an infinitesimal problem. And it turns out that if you look at a wide variety of circumstances, as I spend far too much time doing myself, you need a potential intensity. Empirically, you need a potential intensity of at least 35 meters per second, or maybe 30 meters per second, to get this kind of phenomenon. Well, I'm sorry that it's not easy to read the numbers. We're barely satisfying this here. But what I want you to note is that unlike the tropics, where you have high potential intensity everywhere, here you have it in a localized region. That's not because the sea surface temperatures are warm there. It's because you have this synoptic scale cold low sitting over warm water. So the difference between this and a real tropical cyclone isn't very profound. It's that the potential intensity arises from the process of a cutoff cyclone forming in the upper atmosphere. In case after case after case, you see this. Normally, the potential intensity is essentially zero at these latitudes in winter. So, whereas in the tropics, it's always large. That's not the rate limiter of tropical cyclogenesis. Here, it is high only because you have this cutoff low here. If you look at the 600 millibar humidity, we also know empirically and theoretically you have to have high humidity in the middle troposphere to allow a tropical cyclone to form. You see that it is complex. There are streamers of very high humidity, but there are also pockets of low humidity. This is also very characteristic of this kind of system. Well, here's another completely different case. It's in the Sea of Japan. All right. So this is not a European polar low, but it's a polar low. Physics doesn't care really where you are. Okay. Here is the coast of mainland China. Japan is over here somewhere. And again, you see scale is different because the scale of the picture is different, but you see this sort of eye wall surrounding a clear eye, and the whole system surrounded, at least over water, by shallow to medium depth convection as this cold air is flowing out over very warm water. And we see the same kinds of situations here. So this is the 950 hectopascal geopotential. There, the ERA5 is capturing this surface low. And here it is at 400 millibars. So you have a co-located, look at these closed contours. That's not normally what you see at 400 hectopascal, okay? It's a cutoff low. And later I'll show a case where I'm going to show you the whole evolution of this. It's a transient All right. Not obviously not permanently there. And the potential intensity is quite elevated, up as high as 45 meters per second in the region where the polar low is. And in this case, according to ERA 5, I'm not sure how far I trust the humidity in this, but it's very humid in the region where this low is at good levels. Here is a climatology of such lows. They're not infrequent, not like Medicanes. They happen all the time. They form in the Sea of Japan usually and almost always move out to the east. They're responsible for a lot of snowfall in the northern part of Japan in the winter. Okay, let's move from polar lows to Medicanes. I don't think I'm moving meteorologically. I'm only moving geographically here. Okay, that's what I believe anyway. Here is a picture of one just off the coast of Libya and Crete in December 2005. Same kind of deal. You have deep convection, a relatively small scale phenomenon. And if you look at the ERA, this is actually surface pressure in this case, but you see it captures a strong low pressure system in this region of the southern Mediterranean, co-located with a similar closed low at 400 hectopascals. This is just showing you that these are all similar, and the potential intensity is well elevated over its climatological value, which is close to 0 at this time of year. Okay. It's elevated again because the process of forming this cutoff low, which is an example of Rossby wave breaking, lifts the air in the troposphere, cools it off, and humidifies it, creating a good environment for a tropical cyclone-like entity to operate off the air-sea thermodynamic equilibrium. And you can see that the humidity is elevated there as well, okay? And right there, right. And here is a Medicane of 15th January, 1995. I'm going to have to try to adjust this. It's trying to fall off my head, but let me tell you. Let me try this one more time. If I give up, I'll take you off. Oh, this is a very hurricane-like phenomenon visually in the satellite picture. It's got an eye, with a P formation. But it's in January. Here are some other satellite images of the same storm. Here it is just weakening and making landfall in North Africa. And here is the ERA analyzed surface pressure, 15th January 1995, and the 400 hectopascal geopotential here. In this case, I'm going to show you something about the evolution of this up until the time I just showed you. So we're going back to the 12th of January. Here's 400 hectopascals. You can see the Mediterranean here, Italy, Greece, Macedonia, and so forth. And you have a deep upper level trough, which is 400 hectopascals. At near the surface, 950, you have a complex distribution, but there is generally low pressure over the northern Mediterranean, the region around Italy and so forth. And if we go to 24 hours later, pay particular attention to the upper levels here. You can see a classic Rossby wave breaking event occurring here. It bends back, it breaks. It forms a cutoff low over the Mediterranean. A broad surface low also develops here as the air heats up in the boundary layer. And then you get to the time I showed before. Notice that this cutoff low is weakening, but the surface low is intensifying. You get a very compact low that you see in that image. If you look at the potential intensity, 3 days before the first charts I showed you, 12th January, you can see it's pretty low. I know the scale is very hard to read, and I apologize for that, but the yellows are around 40 meters per second and so forth. It's already somewhat elevated here, but as you go on in time, it becomes more elevated. So you can see these are all the same color scale, even if you can't read what that scale is, they're all the same at least. And you can see how strongly the potential intensity increases as the Rossby wave breaks. Right? This happened over land, nothing would happen at the surface, but it's over relatively warm water. By relatively, I mean compared to the air above it. I don't mean compared to other water somewhere else. And you can see, again, this complex distribution of relative humidity, which reflects the history, mostly the history of lifting of that air, some horizontal advection as well. Subtropical cyclones is yet another name given to what I maintain is exactly the same phenomenon. Okay, it's a name given by the National Hurricane Center to tropical cyclones it doesn't think are tropical in the, well, certain class of not quite hurricane-like cyclones in the Atlantic. Here is one that didn't get a name. It's a subtropical cyclone southeast of Nantucket, Massachusetts. In January, midwinter 2023, it's really the coldest time of the year in that part of the world, and there, yet you have a tropical cyclone. And it's at fairly high latitude. Nothing like the polar lows, of course, but it's not down in the tropics. It's east of the mid-Atlantic states. So there's 950 millibar G of potential on the 16th of January. The thing that looks like a polar low in satellite imagery is here. It's indeed the lowest pressure in the reanalysis, or lowest G of potential. And here again is your big cutoff low in the upper troposphere. You see a pattern here. I haven't shown you the evolution, but all of these really result from Rossby wave breaking, a very, very common phenomenon. Of course, its magnitude changes. So the picture I'm trying to draw for you is you suddenly, you know, on the time scale of a few days, create a thermodynamic environment which you don't normally have at that latitude and place, which is very conducive to the genesis of tropical cyclones locally. Not globally, but locally. And by the way, in the middle of these cutoff cyclones, you don't have very much wind shear. Right? In the center of that, the winds are zero pretty much. So you have all the conditions. You have humid air. You have lots of thermodynamic disequilibrium. You get a tropical cyclone. Now, so here is the potential intensity. Here's the eastern part of the US. Nantucket is there. That star is where the satellite image shows the polar low, or rather subtropical cyclone to be at this time. And you can see, if you look at the scale, that these are very high potential intensities. You'll see it's locally a minimum, by the way, at the center of this. That's because the way you calculate potential intensity, it's supposed to be an environmental quantity. You try to calculate it in the center of an existing cyclone, you get a completely anomalously bad value. You have to discount that minimum there. But it's generally high. There's the Gulf Stream, by the way, where it's very high, but in a very narrow region. And if you look at the humidity, it's the same old thing, sorry. You see this complex distribution. It's generally elevated where the polar low is, but not very homogeneously elevated. It's got all the structure to it, which is interesting. And again, I'm not sure I trust the reanalysis on this point. You have to have some faith in it. But I don't know how far that faith takes me in the case of humidity, which is a very, very difficult quantity to observe and to model, especially away from the surface. And then, if you aren't familiar with them, you're from Hawaii, you certainly are, the Kona storms. That's what they're called, but they occur in the Central Pacific. It's a regional name given to what I think is the same phenomenon. There you see one in this magnificent satellite image, right there. You can see that the frontal system associated with a much larger scale extratropical cyclone has moved off to the east. That's typical. You can see it's in a generally convective environment. You know, we're taught to think that convection is something that happens in the tropics in summer. I want to remind you that some of the most convective places on our planet, by any measure, are in the middle of winter over oceans. But we don't tend often to observe it. But the wintertime oceanic environment, because especially if you have cold air coming off of continents, is very, very convective. You have situations which approximate radiative convective equilibrium that you see in the tropics, except that there's most of the time, a lot of wind shear, which is why you don't get a lot of tropical cyclone development in this. Well, again, it's becoming boring. I hope it is, anyway, because it's really the same thing all over again. There's the surface flow, 950 hectopascal geopotential. There's 400. They're co-located. This guy came from a Rossby wave breaking event. All right. And there's a potential intensity. Unlike some of the other cases, there's a strong gradient. It's always high and deep enough in the tropics. But where this cyclone developed, it's marginal, except that it is locally elevated by the presence of that cutoff low in the upper troposphere. And again, you see an elevated humidity in the center, but there's a lot of structure in the humidity field. So the bottom line here, and I don't pretend to say that these cover all the things people have ever called polar lows or subtropical cyclones or Medicanes. As we discussed this morning, people have called anything that looks like that on a satellite picture. But I'm proposing that from a physical point of view, here I'm talking about a single class of cyclone, and I'd like to stop calling them by different names. I know that's a big ask, but we're scientists, okay? We're not supposed to be focused on particular regions as forecasters at the different story. Okay? But we're really talking about class of phenomena, and we should study them everywhere if we're really interested in how they work. But the idea I'm trying to promote is that these happen when the thermodynamic environment, as measured, for example, by the potential intensity, is not normally conducive to the development of tropical cyclone. Unconducive, or at best marginal. Okay. The approach of an upper potential vorticity anomaly, as I've called it here, I've been talking about it as a cutoff, right? It's a Rossby wave breaking event, leads to massive lifting of the middle tropospheric air. That's a dynamical consequence of the cutting off of the cyclone. Very straightforward quasi-balanced dynamics. I think those of you who've taken dynamical meteorology courses will be very familiar. The lifting cools the air. So now your air is much colder than it was before and much more out of whack with the ocean below it, if this is occurring over the ocean. There's much more thermodynamic disequilibrium. And at the same time, it moistens the mid-troposphere, which also makes the thermodynamic environment more conducive. So potential intensity may be substantially, and often is, substantially enhanced under these cold upper lows. And you can even quantify this. You can develop a modified potential intensity, or V squared, the square of the potential intensity is equal to whatever the background is, which could be 0, minus the difference between the geopotential, say in the center of the closed low, up in the upper troposphere, and that of the surface low if there is one. Okay, and that's just a quantitative way of looking at that. And that can be, for example, in the case of the January 1995 Medicane I showed you, that can easily be an addition of 40 meters per second, 40 meters per second squared, if you will. Normal potential intensity squared. Now, I want to show you some numerical simulations that we've done with an axisymmetric, but otherwise full physics model, the non-hydrostatic convection permitting model of the kind that are often used in theoretical or idealized studies of tropical cyclones. What I say about the model? Well, the difference is we're giving it a far field environment that simply won't thermodynamically support any cyclone development. We start with that environment. It's radiative convective equilibrium, but it's cold, and it just doesn't support tropical cyclones. But we add to the initial condition a cold upper low, just an axisymmetric cold upper low, thermal wind balance, all right, with maximum winds of 20 meters per second, which is actually pretty mild for an upper cutoff low, at 300 kilometers radius. Remember, well, it's continuous, but it reaches its maximum amplitude at tropicals. We're talking about the tropicals here. 10 kilometers up. Yeah. Oh,
closer to your.
I'll try.
Yeah.
How's that? Is that better? Okay.
Yeah, thank you.
Now, if it only stayed there.
It goes down.
Yeah, it goes down after a while. Yeah, so does the talk, but we'll see how that. Okay, so it's axisymmetric non-hydrostatic cloud resolving model that I developed with Rich Rotuno quite a long time ago, although we've improved it a little bit since then. It has fairly high horizontal resolution, but it's been used widely in lots of idealized studies. If you want this model, just ask me. It's not hard. I can give you the whole package. You could even run it on your laptop practically. It's not an expensive model. And so here is not quite the initial condition for some reason when I was preparing the slides, I couldn't find it. This is 1 day after initialization. This is the azimuthal wind. So this is radius from the center. This is altitude in kilometers. And this is the azimuthal wind component. So what you're seeing mostly is the initial condition. We specified an upper or low in thermal wind balance. And the thermal wind balance is shown here. This is the temperature perturbation from the far environment. It's cold in the lower troposphere and hot in the stratosphere. It's a low pressure system that reaches its maximum amplitude at the troposphere. Right? That's the initial condition. And this little lump here is because of what's starting to happen. It wasn't in the actual initial condition. It was day 1. So let's go on 1 day at a time. Well, that's just zooming in now on this azimuthal velocity at day 1. This is day 2. Okay, and the new thing here is that a low-level cyclone, red means cyclonic flow around the axis, has developed inside the upper level cyclone. So I like to call this the Russian doll evolution of one of these classes of cyclones. You have a warm core. This is warm core because the vorticity above the boundary layer is decreasing with height. Okay. A warm core cyclone forming inside a cold core. And I'm not showing you this here, but if you go back to the ERA 5 reanalysis, you can see that. You see this massive, like if you look at 700 hectopascals, a cold pool with a little warm, relatively warm anomaly at its center. Just like Russian dolls, right? There it is. This is the low pressure system that's developing from the same physics that operates in tropical cyclones. Exactly the same physics. It has to be in this model, but it's axisymmetric. There is no other way it can develop. Now, this is a day later. This is intensified and gotten a little bit deeper. And notice that this child vortex is destroying its parent. This is substantially weaker because the outflow of this tropical cyclone-like entity, whatever you decide you're going to call it at the end of this conference, okay, has wiped out the cyclone at the troposphere. It's in the process of doing that. And we see that uniformly. I didn't show you much evolution, but you see that in the data that upper cyclone weakens. Problem is, it probably would weaken anyway. Is it weakening substantially faster than it would have without the surface flow? Okay, by day 4, there's not much left of the upper cyclone. The hurricane-like entity is growing, amplifying. This is wind speed in meters per second. I didn't put I guess I did put it at the top. And here it is a day later and so forth. And by the time you get to day 6, you really have something that looks just like a tropical cyclone, although it's not as deep because the tropopause isn't as high in these conditions. Okay? We're off to the races. All right, now I hope I've convinced you that there is a class of cyclone that operates on these physics. It may not encompass everything people have ever said was a Medicane or a polar low. Now that I have maybe built up a little confidence, I want to throw a little cold water on that by showing you departures from this model, okay? So here is what visually looks like a classic Medicane or hurricane. It's Cyclone Zorbas near peak intensity, making landfall over the Peloponnese in September of 2018. Now, notice it's September. Unlike the other Medicanes I showed you, This is not during the coldest season. It's actually at a time when the Mediterranean temperatures are near their peak climatological. And it looks a bit like a tropical cyclone. And here's a close-up of it. You can see the makings of an eye. This is making landfall in Greece. Here's the track of the cyclone. Okay, it started down here and moved up to the northeast. And here is the potential intensity. Now, what makes this case different, it was already high over most of the Mediterranean when the cyclone developed. How high? As high as 80 meters per second. That's like the tropics. Okay. The situation here is not appreciably different from what you'd find over the tropical oceans. Here is the evolution over some days of the 400 hectopascal geopotential. It looks in some ways similar to what you saw before. There's an upper level trough. It's cutting off, forms a nice cutoff cyclone over the Mediterranean. Okay, it's doing a similar thing. But, and I don't have the slides to show you, it turns out that if you, I have these, but I didn't put them in the presentation. The potential intensity is only slightly modified in this case by the upper low. It's not that strong. So this looks like what tropical cyclone scientists have for years called tropical transition. You have a mild extratropical development that becomes a tropical cyclone. It was already in an environment of high thermodynamic potential. It didn't have to create that environment. So I would say that Zorbas was a tropical cyclone, pure and simple, and catalyzed by tropical transition. It looks just like case studies that have been made in the past. So I would not put Zorba into the classification that I have proposing to, because it's just a tropical cyclone, I would say. And it, you know, occurred in September, at the warm time of year. So classical case of tropical transition, little if any local enhancement of potential intensity by a cold low aloft. Zorba struck Greece, I would argue, as a classical Cat 1 hurricane, and is even regarded that way by the National Hurricane Center, surprisingly. It was the first storm, I think, ever categorized as a tropical cyclone in the Mediterranean by the National Hurricane Center in the US. Why they decided to do that, I don't know, but I think they were right. Whether it could apply to some previous cyclones, we go back and look at the reanalysis data. Here's another variation that doesn't fit the mold. And this is a really recent example, which I think is utterly fascinating. It's Storm Danielle, which someone already raised in the discussion earlier today, this past September, okay? Here it is, just about to strike Tunisia in the southern Mediterranean, okay? It's very asymmetric at this point, but very clearly cyclone with very deep convection. And its track started up here at the surface and came down this way and survived quite a long time over land. As a matter of fact, Tim Houston, whom I've worked with on this case at the European Center, thinks it may have reached its peak intensity after landfall. And I think he's right. Was this a Medicane? Let's have a look, a closer look at this. Well, Tim gave me this chart. It's a little film going from the 5th of September to the 12th. And the, let's see, the green contours are the surface pressure or the 1,000 hectopascal geopotential. I'm not sure which. I think it's the surface pressure. And the red is upper level. I can't remember exactly. Anybody read that? 300 hectopascals. And this is just a loop showing that initially the surface pressure and the upper low co-evolve. They're evolving in the same space. And so in its early lifetime, it looked like what you see in a Medicane, developing under a Rossby wave breaking event. All right. That's what it was like early on. But something weird happened a little bit later. Let's have a look at this again. So here is the 400 hectopascal geopotential. on the 4th of September. And you see this beautiful cold trough digging down over Eastern Europe and into Greece. And then it does what they tend to do under these circumstances is you have a wave-breaking event. The potential vorticity, which I haven't shown you yet, also cuts off. That is the dynamical definition of a reconnection event. It's an irreversible process where PV contours reconnect. It's very irreversible. I'm showing you contours of 400 millibar, which is not a conserved quantity, so you can't formally conclude it's a wave-breaking event from looking at geopotential, but I'm cheating here, okay? It was a wave-breaking event by formal definition as well. And this is the potential intensity. And you can see that it was somewhat elevated already. There's this big trough here. It's September, all right? So it's already fairly high, although it's not high up here in the northwestern Mediterranean. And it's elevated a little bit as this cut off, but not a lot. So this is maybe looking a little bit like Zorbus, okay? But, so it's a tropical transition like Zorbus. Small enhancement of potential intensity, so it doesn't fit the mold of what I've been talking about. But wait, this is what's really fascinating about this case. Let's look at it in detail. I'm now showing you 250 hectopascal potential vorticity at 12 GMT, 10th September 2023. By the way, does everybody know what potential vorticity is? I know you know. Well, in case there are people, it is a adiabatic invariant, which is defined as the dot product of the vorticity and the gradient of the entropy of the atmosphere. And you can show that in inviscid flow with no sources of heat, it's conserved. It's also invertible. That is, if you know the potential vorticity distribution, and you assume the flow is balanced, quasi-geostrophic, whatever, you can invert it to find the rest of the flow in the atmosphere. It's a very useful quantity. And in extratropical cyclones, the interaction of tropopause-based potential vorticity anomalies with surface-based potential vorticity, which is really just the temperature at the surface itself, you can explain extratropical cyclones and say, well, this, I call it a satellite PV anomaly, has swung around the upper low. And at this time, the surface low is just making landfall here. And this is a perfect setup for baroclinic development. Okay, so this is a very unusual case. We cannot explain the intensity of Danielle by looking at the potential intensity. It doesn't work, okay? Something else is happening in this case, and it's the satellite PV anomaly that swung around the upper low, its parent low, and it's nudging the surface cyclone, which probably did develop in the classical tropical transition mold, okay, as something much closer to a tropical cyclone. So let me summarize. I hope I've left some time for questions. Yes, I have left plenty of time. Cyclones in this class form in a climatological mean states that are at best marginal for surface flux-driven development. That is, states which are normally much too dry and have much too small thermodynamic potential for there to be tropical cyclones. It's really a part of the definition of what I'm calling this class of cyclones, which I'm asking you to name if you buy the hypothesis, that they're all the same thing. The approach of the upper low lifts the lower tropospheric layers, cools them, thereby creating a thermodynamic disequilibrium with the surface and increasing potential intensity and moistening the air in the middle troposphere. So it creates locally an environment which is nearly ideal for the development of tropical cyclones, but only transiently and only locally, not globally. And I would encourage you to stay tuned for the talk that Romu is going to give tomorrow afternoon, which will involve how to create catalogs, if you will, of this class of cyclone. and how climate change might be affecting it. So I really encourage you to come to that. So let me end though in an impromptu way by saying that we talked a lot this morning in the discussion section about classification. And I think it's very important that we understand the physics we're talking about. I like the idea of physical classification. I'm going to say something very provocative now, is I don't like any kind of classification when used in the context of real-time forecasting. And I wish we did not have that classification for tropical cyclones today. People have been saying, what do we call these and how do we manage them? I think that's wrong. I think it's moving in exactly the wrong direction, because someone said this, I wish I could remember who this morning, but she was very elegant about saying this. We're worried about hazards for the sake of people. We're worried about hazard. How are we putting people at risk? What the thing that's causing the risk is called is irrelevant. And it's caused a great deal of trouble in history. And I'll give you as an example, Hurricane Sandy, which in 2012 flooded a good part of lower Manhattan, caused all kinds of problems. But there was a lot of fuss and bother over whether it was a hurricane. And so at some point, the National Hurricane Center said it's not a hurricane anymore. And the mayor of New York City called off an evacuation. And he later rescinded that, okay, but probably led to unnecessary deaths. Oh, it's not a hurricane anymore. We don't have to worry about it. Classifying these things in forecasting, in my opinion, is exactly the wrong thing to do. We need to classify them as scientists for understanding them, or at least it may help understanding them or understanding how they're different. But classifying them for forecasting, I think that's going the wrong way. We really have to move toward probabilistic forecasting that ceases to focus on the storm, which is what we do in hurricanes, and puts all the emphasis on people, right? It's a people-centered forecast, which has to be probabilistic in the end. I'll leave you with that somewhat provocative thought. Thank you.
Thank you very much, Kerry. There is room for questions, and you cannot ask a question without having a microphone in your hand. So please raise your hand if you have questions, and I will bring you a microphone. And from the audience that's in remote, you can ask your question through the chat, and we will read your question on the chat, right? You can do? Or you can do, okay. Yes. Take the first one here.
Thank you for a very interesting talk. So in about the cyclones in the Mediterranean, I understood that what you call Medicanes are somehow sort of subtropical cyclone, while cyclones like Zorbas are tropical at the end. And so you can, I understand that the difference is related to the antecedent condition, no, in terms of potential intensity. So can we suggest a sort of seasonality for the occurrence, or the second category, which is probably the most dangerous?
Oh, I think so. I'm not sure I'd want to make a definition that's solely based on seasonality, but I would expect that the full tropical cyclone-like storms in the Mediterranean, like I would maintain Zorbas was, right, probably occur August, September, October, thereabouts, and the other ones more in midwinter. One of the things that's very interesting about your question is it has a lot to do with what's going to happen in the future. Because if you look at potential intensity, that one thing, a monthly mean climatology, which doesn't largely include these excursions I've been talking about today with the cutoff lows. They're in there, but they're not affecting the climatology very much. That you see uniformly the Mediterranean going up pretty fast in potential intensity. So, I mean, if that's common among lots of different climate models. Now, of course, other factors may change in the other direction, but if that's what you're going on, and say there's increasing risk of the more tropical-like Medicanes. But you'll hear more from that from Romu tomorrow.
Thank you very much for the talk. One question I had is, I think one already existing name for these systems is hybrid cyclones. How are you not happy about it? And maybe a follow-up question is, these cyclones, I believe, kind of exist in a continuum of cyclones. So in the end, can we really define a category for them? Do we want to do that?
Yeah, so that's a very interesting question. I mean, it's one thing that the cyclone phase space that you mentioned this morning yourself, I think, was developed by Bob Hart at Florida State, avoids by having a continuous plane in which we classify cyclones. So yes, I do believe there's a continuum, and it's probably helpful to just put labels to the extremes of those continuums, as long as we remember that it's a continuum. It's an interesting question. I don't think it's solved for this class of cyclones. I mean, is there, you have just the tropical kind and just the whatever we decide to call this class kind, or is there really a continuum? I bet that there was, but I don't know that there is without actually running the numbers. The extratropical transition is something I didn't mention, which is well studied and is yet a different phenomenon, but has the characteristics that some of these storms have, is they're operating under both baroclinic physics and surface flux driven thermodynamic disequilibrium physics at various stages of their life. So I wouldn't put extratropical transition into this bin, but of course it's an important topic.
So yeah, very interesting talk. Yes, initially I thought that once you call them Mediterranean hurricane, for example, if you tell a journalist that a Mediterranean hurricane is happening, the first idea of the journalist would be like, well, it's a hurricane like in the tropics, no? When you told them that so you can have like hurricane-like factors in the Mediterranean, and so on, you explain them. But the problem here I see is, for example, for Sorbas. So you wouldn't say that Sorbas is a Mediterranean hurricane, but at the end, for a journalist, it will be the same, no? Because it's a tropical cyclone that can reach a hurricane category. So how to deal with this problem, and also a connection with that is, for example, Seleno, no? the one of the January in January in 1995. At the end, it developed an eye, no, from the satellite view. So it's the same as Sorbas. Sorbas started to an eye started to emerge, no, at the end from satellite perspective. You have convection surrounding an eye and so on. But how to differentiate between these cases of an eye developing from a more mechanisms by like polar laws and so on, other cases where the eye is emerging from subsidence, from convection, like in the case of Sorba. So how to differentiate with this type of cases once you have an eye surrounded by convection? How to say, well, how to differentiate between Mediterranean hurricanes and cyclones that reach hurricanes from the Sorbas mechanism? I don't know if
Yeah, you were clear, but I think there are two questions here, or at least I interpret it as that. So I think the class of cyclones I focused on here and hurricanes are basically the same phenomenon once they get going. They've just been initiated very, very differently. So if they form eyes like tropical cyclones do. However, there's a kind of cyclone that develops in many parts of the world, even over land, which can form an eye, even though they're like purely baroclinic and there's warm seclusion. Okay, so I'm not talking about that. But now it comes to your second question is journalism, and I would say more broadly communicating to the public, whether it's us directly or through journalists. And here I get back to the last statement I made. I don't think those distinctions ought to matter in forecasting, because what you're really trying to forecast is the hazard. If it were up to me, we would say, well, for Athens, you know, the next few days you have a relatively elevated probability of high winds or very heavy rain or something that really, or flooding even, if we are confident that there will be at some level there'll be flooding. This is a really big communication challenge all around that we all have. And I think it's just messed up by what we call it. Where people overinterpret that. Oh, it's a hurricane. It's not a hurricane. Sandy was a hurricane. Oh, it's not a hurricane anymore. Nothing to worry about. I think it gets in the way of communication. And we shouldn't, I maintain, get all fussy about those distinctions which are important to us as scientists. Shouldn't really matter to the public, I believe.
My turn. But thank you for the talk. I have a comment about the second statement. As far as I remember, potential intensity doesn't include relative humidity explicitly in the.
True. It does not.
So moist atmosphere is troposphere is another ingredient we need to attain.
Yes.
With other conditions.
It's another ingredient. Yep.
And in connection with the potential intensity, I didn't catch how you formulate your modified potential intensity. Is that an empirical
No.
correction? Is based on theory?
No, it's just based on, so all you really need to do to calculate potential intensity, the shortcut, this isn't exactly precise. You take a sample of air and you saturate it at sea level pressure and temperature. You lift that saturated part, it's saturated right from the ground, right? It's not saturated at 950. And you lift it and calculate its buoyancy. Now, if you don't change the sea surface temperature, you don't change the parcel temperature. But if you cool off the atmosphere, which in the bulk can be represented as the difference between the geopotential at two levels, you'll increase the potential intensity. That's all. So there's no, the only way moisture enters is in a rather minor way if it's affecting the virtual temperature, which you really want to know, but it's fairly minor effect.
Thank you, Kerry. I'm hoping this works. I'm drawn back to your comments about Prigogine and self-organization. I think what you're saying is what, correct me if I'm wrong, because when I saw your maps, I kept on going in my head, you know, how is this different from tropical cyclones and extratropical cyclones? And it's because these storms sort of make their own bed, as it were. And so is that the fundamental commonality between these, is that they basically create their own high potential intensity and then are really sort of self-generating?
I wouldn't say that they're creating their own potential intensity. I think what's happening is you have a separate process, a baroclinic process of Rossby wave breaking. You see happen all the time, including over land. Creating locally thermodynamic conditions of high potential intensity and high water vapor, high integrated water vapor, within which after that happens, the cyclone development is pretty much like a normal tropical cyclone development.
But not all Rossby wave breaks are going to turn into these kinds of events, though.
No, and it depends upon, first of all, they have to happen over relatively warm water. A very interesting question is what I've shown you are the success stories. If success is you created a strong surface cyclone. I haven't shown you the failures, which is a failure on my part because I haven't looked at the failures. That's a very interesting question. What distinguishes a Rossby wave breaking event over warm water that develops a cyclone from one that doesn't? That's a valid question. I don't know the answer, but it would be a great research problem to pursue.
It sounds like a really good one, yes.
It
Thank
is.
Thank you for the talk. I probably have a pretty similar question. When you say that you have the cutoff low, so basically this is stratospheric air with high PV itself. So the high PV air, the cutoff low, could also enhance the cyclone because of the invertibility principle we spoke before.
Right.
So how could it be different from the Daniel case? That's one person. The other question is that, well, follow-up question. I deduce so it's the vertical alignment that matters. And if it's the vertical alignment, then in your model, it's several days to develop the potential intensity. So the Renan, you don't expect them to be aligned vertically too long.
Right.
So is there inconsistency in time scales or?
Well, I think that the answer to your question is undoubtedly very case dependent. So what I'm maintaining is that the surface low specifically develops directly under the upper cutoff low in this case, because that's where the thermodynamic potential is highest. And maybe the moisture, is high or not. That may distinguish cases that develop from cases that don't. Depends on the exact pattern of lifting and horizontal advection of moisture there. But certainly the potential intensity you expect to be high unless there's a strong gradient of sea surface temperature right under the low. So it's not an accident that they're vertically aligned. It doesn't mean that they have to stay vertically aligned. And if you look at the general climatology and evolution of Rossby wave breaking events, you can have a cutoff low that just sits there for a long time, like over France, making it rain for 3 weeks at a time. But it can also get reabsorbed or just dissipate radiatively. And so all of those possibilities exist over the Mediterranean and over ocean in general, I would think as well. But it's not an accident that this kind of cyclone develops directly under the low law. Now, the Daniel case was different because although it developed that way, it got reinvigorated by a small scale PV anomaly that wrapped around this upper scale low and kind of crashed into the surface low. But that, I don't know how often that happens. But it's probably one of the reasons why the European Center model was relatively successful in predicting that evolution.
Thank you for your talk. It was very interesting. I have a question because I wrote different articles about polar law that say that one of the main important mechanisms for the intensification of this type of cyclone is due to the sensible heat flushes. Yes. For example, I analyzed this type of flushes in Medicanes. And for example, in Medicane like Seleno or Lycosia that occur in winter, the influence of this type of heat flushes is very intense. Yeah. But in Medicanes like Thorbas or Llanos, is more important the latent heat flushes. Therefore, it's possible that the Medicane that develop during the winter season are more similar, for example, that the polar low.
So the question is very interesting. And my answer is it doesn't make much difference at all to the cyclone whether the surface flux is sensible or latent. That might shock you, but there's very good reason to believe that. And if you haven't done so already, there's one paper I encourage everyone to read in this, not by me. I'm not promoting myself. It's by Martin Velas-Pardos and Tim Cronin. It was in Jazz last year, in which they go right back to the classical Rayleigh-Benard problem, which is a famous problem in mathematics and applied mathematics and physics. You have parallel plates. The difference is they do it numerically. They can get to very high Reynolds numbers. And they can get hurricane very similar vortices to hurricanes under the condition that the surface flux from the lower boundary is dependent on the wind speed. That is, it's rate limited not by molecular viscosity. And this is where the Rayleigh people stuff becomes completely irrelevant to the atmosphere, as they have polished boundaries. Real boundaries, geophysical or fractal, they're rough. They have completely different characteristics. And we've known since the 1950s, the convection over such a surface has nothing to do with molecular viscosity. It doesn't enter. Rayleigh-Benard, it always enters. The physicists who study that have been trying to get it to go away for 50 years, and they can't. Anyway, I'm digressing a little bit. If you make it an aerodynamic condition which is appropriate to a rough mechanically rough boundary, and the upper boundary condition is insulating, then the natural form of convection is a tropical cyclone. There's no more water at all, okay? None. You have a big jump in temperature between the lower boundary and the atmosphere above it, and you get tropical cyclones. It's a really, really nice paper because they do all the different combinations of boundary conditions. And the classical ones give the classical result of just ordinary convection at very small scale. But with this combination of boundaries and the wind-dependent surface flux, you get that. So it's a long-winded answer to your question, no pun intended, but it does depend on wind, okay? And I don't think it matters to the physics very much whether it's latent or sensitive.
I believe there is a question in the chat. Davide, would you like to read it to us? Hold on a second, you need a microphone.
So there is a question by Salvatore, I guess Pascal from Bologna. Hi, Salvatore. Since the Z400 anomalies and potential intensity are relatively large-scale features, does it allow us to make some use of GCM, global circulation model, to infer properties or change of properties of this kind of cyclones in the future?
Well, that's a very interesting question, and it's largely going to be the subject of Romu's talk tomorrow. So I won't try to preempt that. But one of the things that Romu and I did in the original studies way back when was to take a shortcut to downscaling GCMs to produce Medicane or polar low-like storms, which was to develop a kind of use a genesis index, which is applied to fairly large-scale fields, like produced by GCM. And the genesis index being high was a prerequisite. It didn't mean that we were going to get a tropical cyclone, but if you didn't have a high enough genesis index, you surely would not get one of these. And use that as a shortcut. Am I describing it correctly? Because it was a while ago, and my memory is to generating this by what we call random seeding. You'll hear more about that tomorrow. So I'm going to dodge the question only because I know Romu is going to answer it much better tomorrow. Yeah.
Any other question in the chat? I think you have one.
Thank you, Kerry, for this very inspiring talk. So I was thinking again back at the Mediterranean, right? So if we start to have, or we think that we're going to have in the future more like pure tropical cyclones, so perhaps still there is also some kind of message that is different to communicate, to convey to our colleagues, journalists, and also to the general public. So there is some hazards for which we should prepare, and perhaps we are not yet prepared. Also, because if these are pure tropical cyclones, perhaps the trajectory is not going to follow anything that we like quest is, can be something else.
Right.
Yeah. So what's your thought about it?
So from the work that's been done across the field on this issue, I think we have a long way to go before we really can say anything definitive about future, except a few things that I'd be prepared to defend. Sea levels going up. That's a no-brainer. It's going up in the Mediterranean and other places, and that means flooding from storm surges, all other things being equal, will be a greater problem. The other is the temperatures going up, which means the same storm will produce more rain. And that's a big problem. A lot of the problem, correct me if I'm wrong, the social problems with Medicanes are mostly related to water. Is that not right? It's not, the wind is, yeah, causes damage, maybe surge, but it's mostly water. And we can be fairly confident to say that a given storm will rain more. You'll see tomorrow, I think, when Romu talks, that the various GCMs give a big diversity of outcomes when you downscale this kind of event. The other thing that might be defensible is that the intensity of these storms in general could get larger, or at least the potential for them to get more intense should increase, generally speaking, maybe with some exceptions. Doesn't mean they'll be more frequent. Frequency, as with tropical cyclones, is still an issue that haunts us, right? Nice teaser, yes.
Nice transition. Are there any other question before this final discussion that's going to happen in half an hour or so? I would like to thank you all very much. Remind you, and particularly Kerry, for his big performance. Keep some energy for half an hour in 25 minutes. But thanks a lot. Let's thank Kerry for a wonderful talk. And we will reconvene here at 3:30 sharp with the journalists in presence and in remote, and a round panel discussion. Thank you very much.
Good afternoon, everyone. Welcome to the panel discussion and journalist press conference this afternoon. My name is Susana Camargo. I'm the Marie Tarp Lamont Research Professor at Columbia University. I'm very excited. We have a very distinguished panel here this afternoon. Here on the right, we have Professor Kerry Emanuel. He's Emeritus Professor from MIT. His specialty is tropical cyclones and tropical meteorology. He's very distinguished, have many awards. I've just mentioned one of them. He is a part of the US National Academy of Sciences. Then next to Kerry, we have Samira Kodayar. She received her PhD from Karlsruhe Institute of Technology, and she's currently head of meteorology and climate research department at the Mediterranean Center of Environmental Studies, and she's lead the Costa Connections on the Future Mediterranean Climate and Science. And then we have Robert Bottard, who is a research director of CNRS. He received his PhD from LMD, École Polytechnique, and he's the director of the Pierre Laplace Institute, and he is the co-chair of the IPCC 7 Working Group 1, which is a very important role. And finishing with, on the left, we have David Paranda, who is a CNRS research director, and he received the EGU Nonlinear Process Division Early Career Award, and he is one of the organizers of the Tropicana, which we're having this month. And he's also doing a lot of work on attribution, and he's leading climate meter on that stream, which is doing a lot of work on attribution of extreme events. So we are starting with one question for each of the panelists from my side, and then we are going to journalists and having their questions. So I'm going actually to start with Robert. What can you expect, do you think, in the next IPCC in terms of like extreme events and climate change? What we can help that we're going to learn new, or are we just going to be more of the same? Just your perspective.
Thank you. What a question. Thank you. Well, IPCC assesses what is available on the table. So we will see, but we already actually see many trends in research. And research on extremes has blossomed in the last 10 years, even a little bit before. So I think we have great expectations, actually. And if you remember, one of the key figures of the report of the working group 1, the one with the hexagons, which is very, very popular. There are 3 parts. Of course, the one on the heat wave is all red, almost. We still have some problem with US too, because US is not does not have increased heat wave, but there are reasons for that. We are trying to we are understanding a bit better that. But also for heavy precipitation and for droughts, we have lots of hexagons which are left empty because simply not because of lack of understanding of whatever, but of lack of data and lack of studies. And I think since these tools, especially the real-time attribution tools like WWA or Climameter and others, we have much more knowledge, much more studies, many more studies now to cover the map. So filling the gap, I think we can do much better. Now on cyclones, cyclones remain a difficult topic because of the lack of depth in time and in observations. But now we have many methods developed to link cyclones with other things, and also to better understand the trends. And we know these are complicated. There are things we know that intense cyclones are increasing in frequency, intense cyclones, and they will continue. But we know also that precipitation is increasing during cyclones, but there is a large gap now talking about other things linked to cyclones. And I'm seeing a lot of studies around also trying to look at the depth of cyclones, the depth of intensity, the trajectories as well, etc., etc. There's a lot of progress in understanding the dynamics in general, so I'm quite hopeful. I think we have promising results for the next cycle. Thank you.
Thank you. Next question for Samira. In the last few years, what have you observed in terms of Mediterranean climate and extreme events? Do you think we have more events in the Mediterranean or not? What's going on?
So thank you very much for the invitation. Thank you very much for the question. So first of all, I think all the audience here has a clear idea of that the Mediterranean is a climate change hotspot. So indeed, it is warming faster than the global average. We are battling and suffering and breaking records continuously. So every month, basically in last years, we have here the warmest summer, the warmest season, extreme year period, the most impactful event, etc., etc. And all this, of course, has really strong impacts on the priority socioeconomic sectors in the region. So impacts health directly and indirectly, impacts energy. We need more. We could have problems with it. It impacts, of course, agriculture and food security with that. So basically, it's impacting everyday people's life. So the conditions in the Mediterranean basically are changing. We have higher temperatures, as was already said, in the atmosphere. We have, the atmosphere supporting a major amount of water vapor. We have the Mediterranean Sea that is indeed warming between 2 or 3 times more than other oceans. That this already has, of course, a strong impact not only in the Mediterranean itself, in the sea, but also in the atmosphere. So the climatology and meteorology of the continental area surrounding the region. And this, of course, this environment is conducive to more extreme events. That is indeed one of the main impacts of climate change in the region. So we are seeing in the last decade, so in the last years, more frequent, long-lasting, intense heat waves in the region, more extreme precipitation events, of course, that are affecting the region very strongly with strong impacts on society. So we have marine heat waves that are not very much discussed, but also have a strong impact in the region. So at the end, what we are seeing is that the Mediterranean or the climate change is shaping the Mediterranean. We are living some kind of new reality, and this, of course, we have to adapt to that.
Thank you, Kerry. Next question is for you. I'm sure that you have seen the seasonal forecast for the Atlantic for the next season are really forecasting a very active season, maybe even breaking the past, historical records. And the obvious question is, do you think climate change is contributing to that, or is just natural variability? Have both a La Nina happening at the same time the Atlantic is very warm. So what's your take of the current seasonal forecast?
All of the above. No, seriously, good question, Susanna. It's if you have not heard the forecasters who do these forecasts are forecasting a very busy hurricane season for the Atlantic this year. And I won't get into my view of these. I think forecasts are misinterpreted by residents of the US and the Caribbean as being something that either they need to worry about the hurricanes or they don't, when in fact the stochastic element of hurricanes overwhelms that signal. One of the worst events in the whole history of Atlantic hurricanes is Hurricane Andrew in 1992, which was one of the quietest seasons we ever had in the Atlantic. And of course, that's an anecdote if you look at the statistics. On to your question about what's behind it, the extraordinary nature of it, I think, is a question of natural variability. It being a transition from an El Nino to a La Nina year, other factors aligning. If there's a climate change signal, I think if you compare what's happening now to, say, the 1970s and 80s, there's no question that by every metric, North Atlantic has higher hurricane activity. But it's often advertised as a signal of global warming, when in fact, all the data I'm aware of points to it being a different, yet still anthropogenic effect. It is a consequence of the Clean Air Acts of the 1970s and 80s, reducing the sulfate content of the atmosphere and leading to a rapidly warming tropical Atlantic. There's a lot of science behind that. That is creating a strong signal. And yet and there probably is a little bit of global warming in there, but I wouldn't want to try to tease it out. That's why I said all of the above.
Thank you. David, the last one is for you. There's a lot of interest on attribution of extreme events. And why do you think we care? Why do we care if the climate change for that extreme event or not? Why is it important? Why is it immediately important? Care about there. Having an extreme event isn't enough that you're having.
Yeah, I mean, I think that the question for attribution for tropical Mediterranean cyclones is something that is really a research question. So until like few years ago, there was absolutely no answer to this question. Is fossil fuel burning making cyclones, single cyclone more intense or cyclones more frequent? So until few years ago, that was an open question. And now we start to have some answer to this. There are the first attribution studies on tropical cyclones that start to come up. And we know that at least for some cyclones, climate change, which means again, fossil fuel burning. So it's us as human beings that are altering the climate system. I think that's why we should care. Yes, is modifying at least the intensity of some of the tropical cyclones. So answering this question is difficult. We have here a young crowd that in the next few days will show us also what they did in their PhD thesis that are like actual new research that we're doing also at the Institut Pierre-Simon Laplace about these topics, that we are trying to build a transcontinental research about this topic. And why we should care? Because there is a question that is very important in our planet, and this is justice, and this is also climate justice. The anthropogenic emissions are not a business of all. Some of the countries, that is also the countries that are represented here in Tropicana, we have also an historical responsibility of anthropogenic emissions. And these emissions are changing the shape of the world, are changing the shape of the Mediterranean, and are changing the destiny of populations that are not the historical emitters of CO2 emissions. So why we should care is a question of justice, I would say. And we should give answer. We should know how the tropical and Mediterranean cyclones are changing with climate change, with the goal of understanding, not of finding who's guilty, but more on proacting, saying like, okay, if this is happening, can we imagine a different future for the Mediterranean areas, for the tropical areas that are subject to this phenomena? And if these phenomena are shifting towards new regions, can we protect these regions against these emerging phenomena? I think this was also part of the Kerry's presentation before. Why do we care? To protect and to act.
So now we're going to move to the questions of the journalists. So we have two journalists. I asked the journalists to identify themselves and their names, where they're from, when they ask their questions. Sebastian is going to be reading the ones online. So if people have questions online, they also should identify themselves. So let's open the floor for questions.
I can. The temperature in the oceans have never
Your
been.
name, Fleur.
Oh, my name.
Sorry.
Sorry, Géraldine Besner, Le Point. The temperature in the ocean has never been so highest. Could you please explain us what is the situation about that and how it could affect the cyclone season, the weekend season?
Who wants to answer that?
Really happy to. Well, thank you for your question. It's an important one. Tropical cyclones turn out to be much more sensitive to regional ocean temperature than to global ocean temperature. That is, if I raise the ocean temperature uniformly, homogeneously around the planet, and we can do that in models, yes, the tropical cyclones will become more intense. But if I raise it by the same amount, let's say just in the Atlantic, the effect is much larger and also affects the frequency of storms if it's local. So one thing that's interesting about climate change is that even though the thing that's forcing it, carbon dioxide, methane, is approximately globally uniform, the response of the climate system is not at all uniform. And it's the pattern of response that's really important for many things, but certainly for tropical cyclones. That pattern effect is really important. Unfortunately, the models don't agree with each other very well on what that pattern is. But it is an advance for science that we know the pattern is important. So that's a step forward, and yet we haven't gone the whole distance in answering that question. So I don't know if I've been very clear in my answer, but there you go.
Yeah, sure.
Maybe just to add something on the conditions of the Mediterranean Sea that I was just saying before, that it's warming 2 or 3 times more than other oceans around the world. So the Mediterranean, what we are seeing in the last years, indeed is an increasing trend. So it's warming faster than it was warming before. And it's also important to maybe say here that the Mediterranean, probably other oceans, is not warming or does not warm uniformly. So it means it's not homogeneously warming. There are regions that are warming more intensely than others. And indeed, the area in which we live, that is the Mediterranean coast of eastern Spain, southern France, et cetera, is one of these regions where we see these Mediterranean conditions changing more intensely. And of course, we expect this to have also an impact on the conditions and cyclonic development in the region.
So on top of this, there is also another important thing, that is this pattern effect we are talking about, mix up basically the natural climate variability with the climate change signal in a fashion that for us is difficult to understand as a research scientist. Because, for example, we heard a lot talking about El Niño, La Niña. This oscillation of the climate system, they have an impact on the region and the frequency of tropical and also potentially for the Atlantic, also on the Mediterranean cyclone. So if we have this oscillation and on top of this, we have a warming that makes also this oscillation perhaps change or explore like new patterns in terms of anomalies, then for us it becomes difficult also to answer this question, what's going on, what is going to happen, because our models are towards the edge of what they have already seen, and climate models are like Formula One Grand Prix. So they have a sort of a track where they simulate things, and then there is the grass, and then there is a barrier. Okay, so in fact, the real world, like if you have a car and you drive Paris-Dakar, doesn't have a barrier. Okay, but the models do have some kind of barrier to avoid that they give us like weird results when they are too far from the track. And so if the real climate is getting too out of track of what the model can simulate, then we start to be a bit blind of what the phenomenon can be. And also we get forecasts that are on the edge of what the model can produce. And this is what we have seen for some hurricane, like Hurricane Ian in Florida, where the weather forecast was a bit complicated to make, to say the least, because of this being at the edge of the model and being in, let's say, conditions of the oceans that were a bit far from what the normal weather models actually forecast.
Okay. You have a question?
I will wait afterwards because I want to.
Yes. I have a microphone. Yes, we have a question from Lucia Musel from Radio France International in Brazilian Portuguese. Maybe for you, Kerry. Lucia is asking, how does the increased risks of cyclone in the North Atlantic that we just spoke about impact southern countries or may impact southern countries? And could South America also be subject to extreme events that are not necessarily seen today because of climate change?
So that's an interesting question. We see almost no tropical cyclones in South America today. There was one that hit Brazil, where Susanna is from, when back in the early
2004.
She remembers 2004. There's not much work on that, but I don't see any reason to think that particular kind of extreme event would change very much. It's a part of the world that's not very conducive to tropical cyclones. But there are other important extreme events that do affect South America, certainly flooding. Many North Americans don't know that there's a problem with severe convective storms in the, for example, the Pampas region of Argentina. And the severe convective storms have not received as much attention from climate scientists as I think they ought to. They're not covered very much by journalists, except when they happen. Of course, they're terrible, but not in the climate arena. Hail does an incredible amount of damage every year, especially to crops. And we're just beginning to understand how those storms might respond to climate change. But that and flooding events is important. But on the tropical cyclones, I don't think that's, my own feeling is that's never really going to be a big issue in South America.
Tropical cyclones are in the South Atlantic and eating South America?
It depends on your definition of an explanation. But no, to be serious, the North Atlantic is systematically warmer than the South Atlantic. And that's the proximate reason. But why is that true? Curiously enough, this has to do with ocean dynamics, that the ocean and the atmosphere both transport heat poleward and so forth. But the South Atlantic is the only part of the world in which the heat is transported toward the equator rather than from it. So heat is systematically transported in the ocean from the South Atlantic to the North Atlantic, which is why, if you will, the North Atlantic is warmer. And that greatly enhances hurricane activity in the North Atlantic and suppresses it in the South Atlantic. Now, this is what I mean by what you call an explanation, because I haven't explained why that current is there. So how far back do you want to go? That I think we should stop there probably.
I just want to mention that the other important phenomena in South America is wildfires, especially in the Amazon. So besides flooding, heat waves, wildfires is another big issue.
Just can add the climate meter point of view. We have covered 2 heat waves and the Brazil flooding event in South America. And for these 3 events, we have seen that there is a strong role of anthropogenic climate change in increasing the intensity of this event. So these 3 studies, the 2 Brazilian heat waves plus the Brazilian floods, are studies for which we have quite high confidence in the results that we've got. And so we are also in contact with some colleagues in Colombia to include them in the climate meter consortium. And we have Susanna also that knows Brazil very well. So it's definitely a region that we target to make more attribution studies, because it's a crucial region, both from of course, a social point of view, but also from a ecological point of view, because there is the Amazon forest, which is an ecosystem that is important not only for South America, but for the entire world.
Yeah, and probably everybody has seen the recent floods in Brazil. Southern Brazil were really intense, and a lot of people died, and it's still, the impacts are still going on. And there was one of the heat waves that David was talking about, got a lot of press because it was during the Taylor Swift concert in Rio, and a person died. And that was the main reason that was a lot of international attention.
Can I ask a question?
What?
Related to what you just said, just simply by rising the temperature of the atmosphere, you have more holding capacity for water vapor, and you just change the entire spectrum of precipitation rates. Can you explain that a little better than I just did, and how you attribute this physical effect to what we are observing?
I think one of the panelists should answer.
The question about the holding capacity.
Yeah.
Yes, it's a thermodynamic flow, basically. So thermodynamics that tells us that the atmosphere can hold 7% more humidity per degree. So that makes actually in a warmer world, that makes this capacity of having more water in the atmosphere and more precipitable water, and therefore more intense rainfalls when storms come. So that is the basic reason. And if we look at actually the rates of increase of heavy precipitation around the world, when yeah, okay. So when we look, it's basically that there's a review paper which came out a few years ago. I think we are basically about 10 to 20%, or maybe a little bit less than 5 to 20%. I can't remember exactly the interval, but basically this is the increase in intensity in heavy precipitation from say 5 to 20%, about that. It may be 5 to 15 or something like that, but it's about the number we expect from the thermodynamics. So there can be local effects like increasing the dynamics of the storms that could increase actually the precipitation intensity. But also there could be other effects, and actually we have studies from France, from Mediterranean. In Mediterranean events, it's quite clear Now, at least for southern France, the intensity of the heavy precipitation have increased about 20%. So this is the numbers we get. We are at rather at the upper end.
No, I just wanted to make a small addendum to what Robert said. It's a very interesting constraint on global mean precipitation, that is taking rainfall averaged over a year over the whole globe, because that cannot go up very fast. It cannot go up as fast as Clapeyron, because it's constrained that the condensation of water vapor, which releases heat into the atmosphere, has to be balanced by the radiative cooling to space. And as you increase the temperature, that does go up very slowly. And that's an addition, because if you look at the extreme events, they do tend to follow Clapeyron, just as you said, but sometimes enhanced because the storms are stronger. That means the weaker events, right, have to be less frequent to compensate so that in the global average precipitation. So what that means in general, and it's really important from a societal, is that both extremes go up. That is the extremes of heavy rain and the extreme of no rain, which is why, ironically, or paradoxically, we get more droughts and more flooding events with global warming.
Indeed, I could confirm this exactly over Spain. So we are clearly seeing the extremization of precipitation on the Eastern Mediterranean, in the Eastern Spain. So we very clearly see how precipitation is happening very quickly, so concentrated in time, but with much more water. This has a strong impact on society, of course, because it leads to an increase in potential for flooding. And the other very question, just exactly what he's saying, what we are seeing is that the number of dry days is clearly increasing. So we have about 4% of more days without precipitation. So I think these two things go together, and it's important to consider that we have more extreme precipitation. We have really more intense droughts. The frequency and the intensity of the droughts has increased dramatically, for example, over Spain. But I also would like to point out the very important local nature of these questions that we are talking here. Even if you look at the coast over Spain, you see that in a question of 100 kilometers, you see two different signals. So it's very, very relevant to have this knowledge, to know locally how these phenomena are changing.
Just to add one thing, because if we look at the last IPCC report, you will not see a very clear signal for the whole Mediterranean, because there is a contrast between the north and the south of the Mediterranean. Over North Africa, the signal is not so clear, and probably because we have a mixture of less frequent conditions which are leading to these convective events. But when the conditions are met, then you have heavier precipitation. But in the end, at the end of the day, the drought is winning on the southern part of the Mediterranean in North Africa.
And just to finish from the point of attribution studies that go very much in the direction of what Samira was saying, and Mireia Ginesta here, she did with us the first attribution studies for the storm Alex that struck south of France a few years ago. And in that case, it's really what you were saying, Samira. In fact, we see that changes in precipitation, increasing precipitation, are localized on the Mediterranean basin that is subject to the wind from the southwest, which means like Provence, Côte d'Azur, Liguria, Tuscany in Italy, and then some other area, even with the storm, doesn't receive rain. Why? Because there are also what we call changes in the structure of the storms. That is one of the subject of this month that we do here, that is Tropicana. And these changes of the storm makes the wheel spin faster, the wind faster, and they push more of these precipitations that is on the atmosphere towards some mountain ranges, creating the flash floods that sometimes can be unprecedented, because in some mountain ranges that is exposed to the wind, we sum up the effects, and some other areas doesn't even receive precipitation. We have seen this in France several times this winter, because Pyrenees Oriental, this part of France that is almost Spain, like it's very close to Catalonia, it's basically was left without precipitation, while the rest of the country was really experiencing floods. So attribution and what cyclones, changes in cyclones are very interesting yet to study, because the effects are completely non-trivial, and this demands research efforts in terms of understanding the theory, understanding how the dynamics change, and also how the impacts are on the Mediterranean. And I think one of the goals also that we have is to imagine the possible, still bright future for the populations of the Mediterranean, even though this phenomena will become more intense. So we have to imagine which future for us.
Okay. Question? Here, any question? No, okay. We can open for the public then, if someone has a question.
Can you play football? Score. My question is for Robert. You talked about the hexagon beehive plots in IPCC. In your paper, recent paper, you showed that local circulation changes that weren't necessarily captured by CMIP class models were responsible for heat waves in Europe increasing more than elsewhere. You mentioned in the Eastern US, they're decreasing less than they are. They're decreasing in some places, not even increasing. That perhaps that's related to circulation changes in the North Atlantic. Can the methods that you showed in your paper be applied to that problem? Could we use your methods to find circulation changes that may be responsible for that?
Yeah, thanks a lot for that question. Actually, we are touching difficult questions, because indeed, while models on the global scale simulate quite well the warming, when we look at regional scale, things are a little bit different, and sometimes, like maybe I should explain the background of your question. In Europe, in Western Europe is probably the area where, except maybe polar regions, heat waves are increasing the most. And it turns out that Eastern US heat waves are not really increasing. And it's probably the only region of the world where they are not increasing. So we were wondering why we have this phenomena, and actually it's very much linked between competition between two effects. First effect is a thermodynamical effect, global change in temperature induced warmer and more frequent heat waves. But at the same time, the dynamical conditions for heat waves, which are well known for Western Europe, are anticyclonic conditions with, in particular, southerly winds. When we have these days, which are the hottest day of the year, and it's probably the same in Eastern US as well. Actually, we have more and more favorable situations in Western Europe. And now there's another study by Mr. I think Singh and Eric Fischer, the Swiss from ETH, showing that the opposite is going on in Eastern US. That is to say, we have less and less dynamical conditions favorable to heat extremes. So that could be part of the solution. But as usual in climate, we never have one explanation for one observation that we have. It's always more complicated than that. It's probably part of the explanation why we do that. But the problem is that, as you say, the models are not making really these regional differences while they are making the global one. So that remains a bit a question that we need to solve all together. And I think the work that many of you I see is probably helping that. Whether we do not know whether this dynamical part of the trend is a response to climate change itself, or whether it's natural variability. It's probably a response, I would say, that is not well captured by models, but it could also well be an effect of long-term variability. Variability is not only 1 year after another. It can have also long-term trends. I hope I was.
Other questions from the public?
Thank you. This is a question for Kerry, Emanuel. It occurred, so there was a question, and you mentioned the seasonal forecast for tropical cyclones in the North Atlantic for the next season. So I guess that we'll follow this on the TV from France and see how the Caribbeans on the Eastern US are affected. But this is what we'll see on the TV. My question is related to a question that came before. So could we expect in the near future or the long-term future something like this happening in Europe? So I mean tropical cyclones that should have made landfall in the US or the Caribbean, but go to either Portugal or Spain or France or Ireland or Europe. There was a paper like this 20 years ago or something, but nobody got back to it. But are there news about this?
I'll make my panel chair here, and I actually asked Luigi to talk about that because he's leading a big project about that, and then I'll let you follow up. Is that okay, Kerry? Come on.
Yes, in fact, we have a project between Pierluigi Vidale from the National Center for Atmospheric Science in the UK. We do have a project funded by the Natural Environment Research Council in the UK and the NSF in the US, and Susanna is part of that. And that is precisely the question. And some of the question has to do with the way we look at data. Because we heard it this morning, the National Hurricane Center until recently looked up a certain line or longitude and said, well, this is not our concern anymore. But if you look back to the historic facts, and particularly more recently when there are no more geographical barriers, there have been some prominent cases of things that arrive very close to Europe. Some of them do arrive with a warm core, make landfall. There have been a lot of near misses. We had Ophelia 2 years ago. So again, going back to the recommendations today, do we care about names? Do we care about particular geographical boundaries? Or do we care about the danger to people? And in this project, we started with what does it mean for the people? So if these storms make landfall with this nature, that nature, what is the main hazard and how does it develop? So 24 hours before landfall time, 12 hours after and all that, what is it people should be more threatened, worried about? Is it the wind? Is it the storm surge? Is it the precipitation? And what should people do? So we're going to study this, and we're going to catalog all the storms going back to weather forecasts, which are huge ensembles, seasonal forecasts, which are also very large ensembles, and reanalysis and historic data, and specific simulations of very specific storms that we can redo thousands of times. To answer, what is the risk of such things? And it goes all the way to what impact we can make.
Thank you, Pierluigi. Kerry?
I have very little to add to that excellent answer, except one small thing is that hurricanes coming up into the Western Atlantic, as they often do, and travel toward the pole, can excite disturbances in the atmosphere that are not hurricanes, but can cause big storms in Europe downstream. And a good example of that was the terrible storm that devastated southern England in October of 1987, which was not a hurricane or anything like a hurricane, but there were influences in the atmosphere that could be traced back and were by British scientists to a hurricane, not a very notable one, that occurred in the Western Atlantic. So one thing we need to research are these indirect effects that hurricanes may have on the sorts of storms that you normally have in Europe, but could affect their frequency or intensity.
Yes, to make this point even stronger. So many of the storms that we have in Europe and in the Mediterranean take their source of humidity or water back into the tropics. Okay, so it might be this Tropicana conference that we have here. We just talk about the Mediterranean locally or the tropics, but in fact the climate system is interconnected, and we have things that we call rivière atmosphérique, the atmospheric rivers that bring us a lot of moisture from the tropics to Europe. And even from the point of view of attribution studies and some other studies that will come up soon from our brilliant students, show us that a strong component, even of the floods that we had in France or the snowstorm that we had in Bavaria during the winter, this moisture, this snow, this rain comes from the tropics. So we can trace back. The tropics for us is the Atlantic tropics. Which proportion? That's the question, and that's the important question. And for this, it depends. The question is depends. It depends. We can see then in the attribution studies, for example, when we have that we add on top of what Robert was saying, like this 5–14%, we had 20–30%. When we double the amount of rain that we can attribute basically to the changing climate, then it means that this double amount has been transported from somewhere to Europe, and then this transport is most of the time a role of the atmospheric rivers that are also enhanced by the climate change. And this is true for Europe, but it's also true for another region that looks like the Mediterranean, and it is California, for which what Samira said, drought more severe and more severe also extreme precipitation also applies. So
maybe just complementing what David said regarding this proportion of water vapor that really fits, let's say, the convective storms. If we go to convective storms in the Mediterranean, what we know is that in this region, more than 50% of the water vapor that fits convective storms comes from somewhere else. So it's not from the Mediterranean. So I think this gives you an idea of how relevant these kind of situations could be. And to give you an example, for example, in 2018, I don't know if you remember, but the ones that were in the Mediterranean, we had really strong floodings that affected, for example, Balearic Islands very strongly. We had several fatalities and a lot of really strong economical damages. So we know for sure, for some studies that we did, that the presence of the Hurricane Leslie was one of the key pieces for this extremization of already an extreme period for the region.
More questions?
Thank you.
Yeah.
Can you hear me? Okay. So I'm going back to the stone thrown by Professor Emanuel before about nomenclature. So he was saying that you were saying, if I got it right, that forecasters shouldn't label storms because this might give some wrong information out to the public. But at the same time, I've always thought that it was kind of that the public likes names and that it's also useful sometimes to bring out names so that people can kind of have a mental association between the names and the impacts they expect, as for hurricanes, for example. So yeah, this is actually a question for everyone, not only for Professor Emanuel.
I guess I'll start. So I want to make a little bit of a distinction between a name and a label. I'm not quite sure which one you meant. Name is when they give it a name, Dolly, Hurricane Dolly or something. So
No,
you
a
didn't
label.
mean that. You meant
No,
a
no.
label, what kind
Yeah.
of storm. Of course, at some level, they're very important, right? People should know whether what's coming at them is a hurricane or a tornado, for example, to take an obvious thing. But my point is that distinctions that don't really matter for the kind of risk, like whether it was a pure hurricane or whether it was kind of storm I was talking about this morning, which is kind of a hurricane but instigated differently, whether that matters to the public. And there's got to be a line drawn. But I would say the larger issue for me is we meteorologists, we who love weather and study it, are, of course, by definition, we're focused on storms. And yet, when we give people forecasts of high winds or heavy rains that aren't associated with a well-defined storm, and that happens often, we naturally don't focus people's attention on a storm. We say there's a 60% chance that you'll experience high winds this evening, which is directly addressing the hazard to them. I mean, it can be more detailed than that. But whether that was a result of what I would call a tropical cyclone or an extratropical cyclone or a hybrid storm may not be so important to the public. And the only thing that sticks in my mind, and I gave an example earlier, are cases where that demonstrably led to the wrong action. So for example, this Hurricane Sandy, when before it hit New York, it was downgraded by the Hurricane Center to be not a hurricane, still very powerful, dangerous storm, very, very broad in its wind field. The hazard didn't decrease at all, but lots of people thought it did. And that's what I'm trying to avoid, I guess.
Yeah, so
Yeah.
maybe it's also about the wording that the forecasters put to that, because they could have called it an extratropical storm with hurricane-like hazards. And I don't know, that might have kind of kept the light on, the emergency light on, I don't know. Yeah.
So there are people in this audience who are more knowledgeable about this than I am, but my understanding of the way this is done in the UK is that they have a system of 3 colors. I think it's like orange and yellow and red that describe the level of hazard. And then there's a way to drill down from those basic things. Red is you better jolly well pay attention, right? But if you want to have more information, you can get it. You can drill down. And I think that's something to be said for that level of education. Make people focus on the hazard to them and not on the storm. We love storm.
Yeah. Yeah,
It doesn't necessarily matter to that. That's my point.
Okay, in the queue.
I just wanted to add something as a European who at some point in life decided to move to other countries, and one of the countries was the US. I remember distinctly that when the European Center started to issue forecasts, there was a fantastic forecast of weather in Italy. and they forecast a convective storm, which was extraordinary at the time, that hit Piemonte. It meant that a canyon in Piemonte filled up and massive amount of water came through the canyon. People drowned in their cars. At the same time, I moved to the US and I was living near Boulder and I went up the Great Thompson Canyon and I saw all these signs saying every few kilometers or even every kilometer saying with a picture said, in case of flash flooding, climb to safety. And there was a picture of somebody going up the slope and getting out of the region that would flood, okay? And this to me struck home. It's pointless to tell people this is the name and this is this storm and that storm. If people don't know what to do, and this is the same in Japan. I go to Japan all the time. There are signs everywhere, what to do when there is an earthquake, what to do when there is a typhoon, where to go, what is the assembly point, how to behave. And to me, those people died needlessly. The forecast was perfect. It just didn't make any difference to those people. And I think in the US, there is a strong culture because, you know, the weather is very severe there and all that. But also people respond to these names. They've been trained. They've been through the exercise. And they see on TV, because the US is a big place, see on TV people in Florida boarding up their windows and this and that. In Europe, we have this idea that weather is sort of curiosity, but it's not that serious. But particularly, we don't know what to do. And I think, again, I want to say, I agree with Kerry. We need to tell people how to act. And this is the individuals, the businesses, decision makers, and all that. And not so much what interests us as scientists, what phenomenon it is. This we use to get there, but we need to go all the way to telling people how to behave. Otherwise, it's a bit pointless. Yeah.
Well, I think that as in France, at least thanks also to our friend journalists, I think now this culture is kicking in finally, because there is a lot of coverage of extreme events and there is always a nice synergy between the climatologists that say, is this hazard increasing for the population or not? And Meteo France, which is now an amazing warning system that works quite well. And I give you an example that is relevant for Tropicana, is a cyclone Belal in La Réunion. No victims, very useful alert system with 4 colors, so including a violet color that was basically no one moved, including the force de secours, like the people who can bring help. And that's actually a very striking example on how things can work well. A counterexample of things that could work better, it's the last, and this is interesting also for us, is one of the last episode 7 all, the floods in south of France, 7, that was not as extreme as the one we had in autumn, but it made more victims because this was on the judgment of the people and orange alert level. So there are some bridges in this event that are that can be flooded, and you have the panel, the panel that Pierluigi you were saying, like, don't go if you see that there is rain, but then the people actually estimate that it was not so bad, and because there was I mean, it was not such a strong event, okay? And in this case, I think there is still room for the discussion. When it's extremely extreme, then we start to know how to behave, but in some case that is in between is extreme, but still perhaps I can go. And this is true for thunderstorm, for cyclones. Then I think that we can perhaps communicate a bit better. There are hazards, and that the caution must prevail on we do the activity. True also perhaps for Taylor Swift concert.
To continue working by example, maybe 2 of the events that cause the most damage, both for life and for structures, are Sandy and Katrina. And my question to you guys is, and you girls, what are the progresses we have made in the last 10 years in predicting the landfall of these events? Can you tell us how much better can we predict them? Are we able to forge a response to these events in a way that give time to people to shelter or to move away from the event. And the same question maybe applies to flooding, because I don't know, it's because of the news coverage, but in the last few years, this flood event seems to be a lot more covered. Is it that they arise at a higher frequency, or is it just that they appear much more in the news than we used to report them?
So I'll have a crack at answering your question, very interesting question about that. If you look at the tropical cyclone forecasts, you look at what we call the deterministic forecast, the single track. The official track by objective skills gotten better and better and better over the last 4 or 5 decades. It's a really unsung accomplishment of science that we're getting better at that. The intensity forecasts, how strong the storm is at landfall or how much rain it produces, have increased very slowly over that period and erratically. So we haven't done so well. But I think the really big increase is almost never, big improvement has never talked about, is that we've learned how to do this probabilistically. And I cannot emphasize how important that is, that there's always uncertainty in forecasts. And the uncertainty is state dependent. You may have a hurricane 100 mile, 100, 200 kilometers to the southeast today, whose track is very predictable. The ensemble spread is very small. And the next year, same kind of storm, same place, very low predictability. We are getting better and better at that. And yet we have not figured out how to communicate this information. And to me, that's a big, big tragedy. And I'm often told by people, even people who are forecasters, we don't do that because we don't think the public can understand that. And I'm not ready to give up. And what's interesting is that, I hate to say this, it's probably particularly true in America, but where money is involved, they've gotten very clever at using probabilistic forecasts. So let me just give one quick anecdote about this, which I think is kind of a fantastic one. When Hurricane Andrew happened in 1992, there was a huge episode of what's called price gouging afterwards. That is, there's a huge demand for water and lumber to rebuild. And so the price went through the roof. You could drive a truck full of bottled water from California to Florida and make a fortune. And they were talking about passing laws against that. They didn't need to. It turned out that the companies that supply water and wood and all that figured out how to use probabilistic forecasts. I sat next to somebody who ran such a company on a plane once, which was a happy accident because I learned this. He worked for a company that supplies lumber. It's a chain all over the US. What they do is when they look at probabilistic forecasts of the probability of damaging winds exceeds a threshold, they ship lots and lots of lumber to shops, their shops, which are just outside the area of expected damage. And then when the damage occurs, it's rushed into the area. And so we now have the opposite of price gouging. The prices actually go down. And that's a success of probabilistic forecasting. It's also a tragedy because we haven't been able to learn how to use that to save lives. You don't have to convince lumber where to go or people to ship it. You do have to convince people to run up the side of the canyon or do something to save their lives. I mean, to base their decisions on probabilistic information is just not something we have solved from a communications standpoint.
Can I add something about Katrina and forecasts in general? We can have huge, perfect, beautiful forecasts. If we're not prepared for them, doesn't matter. In the case of Katrina, the impacts were really due to the levees and the infrastructure problem. So it doesn't matter you have a wonderful forecast. If your infrastructure is not ready for that forecast, what's the point? You know, you have the forecast for Harvey. It was, spot on. And still we have, the flooding that we have and the construction that continues, the development that continues to happen. So I don't think that we can forget the side that what are we doing? Yeah, we have hurricanes in Florida. We can have the same hurricane that was 100 years ago. the impacts in Florida will be orders of magnitude larger, just because what? We are putting more people, more infrastructure, so is, yes, we are here talking about the hazards, we're talking about how improving forecasts, but it's as important or more important to think in terms of the exposure and the vulnerability, what we're putting the people in the way of this storm. And we have to act on that side.
Addendum to Katrina is there were approximately 1,500 people who should not have lost their lives because the forecast, just as we said, was good. And this comes to the point that the communication is also local, has to be local. Doesn't work, what works in Miami won't work in New Orleans. In New Orleans, the whole city government is corrupt, and the mayor, I've read fantastic and depressing books about this, was so afraid of being sued by businesses if he ordered an evacuation that he put off the evacuation by 24 hours. And the school buses that they had said logically in the summer, they're not being used for school, would evacuate. People weren't used because there was a rule you couldn't move the bus before somebody checked the pressure in the tires and that person wasn't available. It was one of the most horrendous acts of political irresponsibility, but it reminds us that the communication of our scientific information that one may work beautifully in New York fails utterly in New Orleans. And there are other cases where tragically we sent in, the National Guard in the South and Central American countries, I think it was Nicaragua, to tell people to evacuate when they were afraid, much more afraid of the police than they were of the storm. If we'd sent in the clergy, not something that we're trained to do, right? People would have listened to them, though we would have saved a lot of lives. So this whole social science aspect of communications, we haven't really engaged to the extent we should. So important.
Thank you. I'm being reminded that this session is for journalists, and they would like to interview you to interview the panel on one-on-one basis at this point, or just the panel and the journalists. So I think we are gonna call this session. I'm sorry, we have some constraints. We're gonna call the end for this round of questions. I would like to thank everyone for absolutely great questions. I think we had and particularly the panels for being so lively and so complimentary in their answers and be very didactic. It was very easy to follow. Thanks a lot to the panel. And we'll keep some time for the journalists to interact with the panel. Thank you very much.
Be also for the journalists, there will be also in French file with like a dossier de presse, and we can translate it, of course, with some elements that will help you to guide you through what we've said, and that we are available in French, the two of us, and in English or in Spanish, in Portuguese. I don't know, Kerry,
many of us,
Italian, but
il y en a beaucoup qui peuvent faire une traduction simultanée. Many of us can translate real fast. So if you want to interview any of the panelists, we'll be happy to assist you just in the translation. I will not interfere with your interview.
Yes, and just for the Tropicana before they run, I remind you that tomorrow the poster session will be earlier than what is on the programs. It will be around 4:30. Okay, so yeah, thanks a lot.
Thank you.